So what does that mean? What does balanced trees mean? So I'm going to show you a couple of examples, and then you can tell me whether these examples shows whether a tree is balanced or not. Imagine you had a tree like this, A, B, C, D. Okay, is that tree balanced? Balanced? You can write on the chart. Do you think this tree is balanced? Somebody says yes. I don't want you to think about, so for this part of the conversation, I don't want you to think about balanced, like, you know, understanding trees and everything else. I want you to think about it from, from a layman's point of view, whether something is balanced. So if you saw a tree looking like this, would you say that that tree is balanced? From a layman's point of view. Okay, a lot of people have said no. Why? Okay, well, there's nothing on the, so layman terms again, there's nothing on the right, on the other side. So there's nothing on the other side. Okay, there's nothing on the other side. So that's not balanced. Okay, a couple of things. Supposing I did like, again, this would say, well, it's not balanced. It's not balanced as well because, well, there's nothing on the other side as well. Is this tree a BST tree? This one, is it a BST? Is this tree a BST tree? It is a BST tree, yes. Why? Because for BST trees, if we have a node X, so key of node X, key at a node X must be greater than keys on the left, and it must be smaller than the keys on the right. Okay. So key at node X means keys on the left-hand side are smaller and keys on the right are bigger. So this one is a BSC trees, but is it balanced? Okay, not balanced. It's not balanced. Why? Because, well, it looks like all the nodes are on one side. If we were to think about such complexity or complexity for operations, so if you were to think about time complexity for operations, we have already seen what time complexity involves. What would be the time complexity for searching, you know, the worst case complexity for searching at an item here on this tree? If you don't remember these, maybe we should take a small example and say, if I was to looking for item 5, supposing I was looking whether 5 is in this tree, how many comparisons would I have done to see that 5 is not on this side of this tree? How many comparisons? 5 comparisons. Well, yeah, comparison 1, comparison 2, comparison 3, comparison 4, right? I've done 4 comparisons and then realize, well, we don't have 5. So this tree has 4 items. I've done 4 comparisons. So what is the time complexity for basically ensuring that 5 is not in this tree? What is the general time complexity at the worst case? If you remember from, yeah, well, it's 4. So in general case will be O of n. So if we had n items that we are looking for, you know, if we have to do n comparisons to find that 5 is not there. So at the worst case, we have to do O of n. Now, looking at this kind of tree, This tree is like what? What does this tree remind you of? Something that we have learned in the past. Who does this tree remind you of? A tree that looks like this. What does it remind you of? A linked list, yeah. So this tree is no better. So this tree is no better than a linked list, right? So this tree is no better than a linked list. Okay, so this is not too good because our search takes this time. Now, I'm going to redraw this tree again here. 1, 2, remember these times are on 3, and 4. And we say, well, this is a BST, but time complexity is, the worst case is O of n. Now I'm going to draw the same tree, or rather a tree similar to this with the exact number of nodes the same way, and then we see what complexity would be. So supposing the root of this tree was 2, 1 then would be this side, 3 would be here, okay, and then 4 would be here. Now, how many comparisons would we now need to do to ensure that we don't have a 5? Right? So we don't have maybe to do comparisons with 2, comparison with 3, and comparison with 4. Basically, we'll just check on the right-hand side. If we are looking for 5, then check on right-hand side only. We'll check on right-hand side only. So the height of the tree here, the height of this tree here, so our search, so remember, we are searching both cases. If we were to think about the height as the one we search with, here the height is 4, so we search with 4 this side. Here, the height of this tree is 2, right? Remember, the height means that there is a number of edges from the root to the farthest leaf node. So the height here is 2. Here the height was 3. So by making this tree short and dense, we then have smaller search time, smaller search time. And we say normally when we search with O of H then is O log of n, particularly for this kind of tree. So we want to maintain log of n, and if log of n is being given leading by our height, we want our height to be as small as possible. Okay, that takes us to motivation number 1 then. Motivation number 1 for wanting to have the trees balanced. Motivation 1. Meaning that, okay, we would like to be able to perform all operations. We want to perform all operations with big O, at the worst case, big O, so log of n. Right? So we want to be able to perform all operations with O log of n. When I mean operation here, I'm talking about searching for some item, adding some item, deleting some item. Well, we'd actually want also to be able to merge. If we had the 2 trees, we'd want to merge with O log of n. We'll see that later. But for now, if you're just thinking about these operations, searching for an item, adding an item, deleting an item, we'd want to be able to perform these operations with big O log of n. That's our motivation for doing a balanced tree. Okay, so number 2 here, I would say that balanced trees, a balanced tree, okay, then in this case, it's a tree that maintains some sort of symmetry, right? Maintains some symmetry. It's symmetrical in nature, right? Right? So we want a balanced tree is a tree that means some symmetrical or some symmetry. I should say that. Some symmetry. So a balanced tree is a tree that would maintain some sort of symmetry. That's what we are looking to do, to have a tree that maintains some sort of symmetry. So from our reading then, or in programming rather, there are a couple of ways then that we can do or build these balance trees. Okay, so we can say techniques to implement them. To implement balance tree. So tell me, which one have you read from the book? Techniques to implement balance trees. Which ones have you read from the book? Okay, so from the book, we possibly read AVL trees, and we possibly also saw red black trees. Have you seen these ones? AVL trees and red black trees? Okay, so you need to go to the chapter. If you not read these, you need to go to the chapter that we have been leading for balance trees. And there are two techniques, AVL trees and red black trees. For the purposes of assignment and assessments, we are going to be working with this one, AVL trees. I would like you to read about red black tree, not because we are going to examine you on it, but because it's good for you to know. And because if you go for interviews, they might ask for you to be able to know this. So there are two techniques mainly that we can talk about. There could be others. AVL trees and red black trees. From the reading, could someone tell me what does AVL mean? What does AVL mean from the reading? Yeah, what does AVL mean from the readings? From the readings, all of you have been reading, what does AVL mean? Okay, I don't remember. It means self-balancing. Someone else? So these are, it comes from the people who came up with these. Anderson, Velsky, and Ladis. So these are the guys who came up with this technique. So it's named after them. Okay, so I know for most of you, basically that you just got the jargon of how it works, but it's named after the guys who came up with the actual technique. Okay, Anderson, Velsky, and Ladis. Okay, the guys who come up with this. It's called AVL trees. And what does it do? Okay, so these are self-balancing. The technique is self-balancing binary search tree. So number one, we should know is that AVL trees are BST trees, right? We already know what BST trees are. BST trees are binary trees. BST trees are binary trees which have ordered property with ordering property. So BSTs are binary trees with ordering property. We already know that. Okay, so BST trees are binary trees with some ordering property where if we have a key at node X, key at node X is less than keys on the right, and key at node X is greater than the keys on the left. Okay, so now we're adding something else to it. So if you remember this idea, from the beginning, we started talking about general trees. And after talking about general trees, we then talked about n-array trees. And from n-array trees, then we started saying, okay, so we got n-array trees. Then we talked about binary trees. And from binary trees, we have been building that journey. So initially we said, well, we can put things in a binary tree, you know, for hierarchical references, but then it will not become any good than any other tree we have because the search will still be O of n. So we started thinking that, well, we could make some ordering property, which we call binary search trees, where we have this sort of relationship. And if we do have that, then it means we can be able to search with O log of n and do a lot of operations with it. Then we are seeing that sometimes when the tree is skewed on one side or the other side, for instance, this kind of trees that we had before, then those trees are no better than linked trees. So again, their search will be O of n, and therefore we want to be able to still reduce that to that. And we said maybe the cure then is to come up with short and dense trees. You know, they are short, so their height is minimized, because when we have a minimized height, then our search is going to be also being minimized because we are starting with big O of h. Okay, so that's where we that's how it is. So with the AVL trees, so now discussing AVL trees, properties, AVL trees, talking about the properties for this, properties. So number one, this tree is, so number one, this tree is a BSC tree with all the properties. Okay, recall the properties, which we just said a few minutes ago, right? We call the properties, the BSC trees. So that's number one. Okay, so that's number one. Number two, then this tree, we have something called balance factor. Balance factor. So the balance factor basically determines, okay, a value, a single value, basically, a single value that determines what, so maybe you could even say here, whether, okay, a single value that determines whether a tree is balanced at a particular node. Okay, so we have a balance factor. I'll call it here BF, not best Fred, but just BF. So BF, a single value that determines whether a tree is balanced at a particular node. So how do we calculate BF? We say BF is equal to height of left subtree, height of left subtree minus height of right subtree. Okay, so how you calculate that? For each node, you check the height of left subtree minus the height of right subtree. And for the tree to be balanced, or for the BF to be correct, for the tree to be balanced, this value might be -1, 0, or 1. Okay, now for the tree to be balanced, the balance factor must be -1, 0, or 1. So if at a particular node, the balance factor is greater or less, if it's greater than 1 or less than -1, then it means that the tree is not balanced at that particular node. Do we have questions so far? Questions so far? Okay, so to recap, AVL trees, the properties. Number one, the AVL tree is a BST tree. So recall the property that we just saw a few minutes ago. Then we're looking for something called a balance factor, which basically a scalar value, okay? Just one value. Maybe I should have said here, so scalar value, okay? So a scalar value that determines whether a tree is balanced at a particular node. And how you get that balance factor? You get height of left subtree minus height of right subtree, and the value should be -1, 0, or 1 for the tree to be balanced. If it's less than -1 or greater than 1, then the tree is imbalanced. Now let's talk about this for a few minutes actually. So if we have balance factor is given by height of left subtree minus height of right subtree. If you want to think about this for a few minutes, right? So if the balance factor is negative, what does that mean? If the balance factor is negative, means tree is skewed on which side? Yeah, on the right hand side. So someone said that on the chart, right hand side. Good work. Right? So if it's negative, right? If it's it's negative, it means the tree is skewed on the right hand side, because it means that the number here, the number on the left hand side is smaller. That's why it's negative. So when the BF, the balance factor, is negative, it means the tree is skewed on the right hand side. If the BF is positive, in this case, right? We can formulate this. We could have said height of right subtree minus height of left subtree, vice versa. The idea is that we, using this negative or positive, we can be able to know which side of the tree needs work or is not balanced. So here we say BF, okay, less than 0, which means that it's negative. That's what it means. Here, if BF is greater than 0, which means it's positive, tree is skewed on left side. And you'll see why this is important, right? You'll see why we want to have this kind of formulation. So now we know that if the BF is negative, the balance factor is negative, tree is skewed on the right hand side, and BF is positive, tree is skewed on the left hand side. Let's do a couple of things now. Example 1, let's deal with height. Example 1, let's deal with height. Well, because we say that these trees are BST trees, so we're just going to do a BST tree and then just label height and BF, and then we label height and the balance factor. So this is not us trying to solve this problem, or this is not us trying to bear on the problem of balancing. This is just saying an example of what is height and what is balance factor. So give me some numbers so that we can build a BST tree. Give me some numbers on the chart so that we can build a BST tree. Okay, we got 10. So 10 comes in here. 10 is the first number. Then we got 8. 8 will go on this side because 8 is smaller than 10. Then we got 41. It will go on the right-hand side here. Then we got 15. That will go here. Then we go 3. 3 will go here. Then we got 27. So 27 will go here. And then we got 42. So 42 will go here. That's a BST tree. If we were to perform a pre-order, just to make sure that we know what we are doing, if we are, maybe not a pre-order, let's do an in-order traversal. If we were to do an in-order traversal on this tree, could you tell me the values, what the values will be if we were to do an in-order traversal on this tree? Well, we know an in-order traversal will sort out the tree. So we'll go to 3, then 8, then 10, then 15, then 27, then 41, and then 42. So an in-order traversal would actually sort out the tree for us, and we know that, so we know that the tree is actually correct. So let's try to write these things. So I'll take another pen here. I'm just going to do heights first, and then we work from there. So what's the height of 27? Height of 27? Remember what we said height is. What is height? Okay. Remember this, recall this. Height of a node X. Height of a node X means, okay, number of edges from that node to the farthest leaf in its path. Farthest leaf on its path. So if we look at 27, there are no edges coming from it. So the height of 27 is 0. If you look at 42, there are no edges coming from them, and therefore is 0. If you look at 3, there are no edges coming from it, and therefore the height is 0. Moral of the story, height of a leaf, you can say height of leaf is 0. Correct? Height of leaf is 0. Maybe you could also qualify something else. So if the height of leaf is 0, what is the height of an empty node? Null. What would be the height of null or a null node? Height, one that does not exist. If the height of one that exists, which is a leaf, is 0, what do you think would be the height of null? Like, remember here we also have like things like this, right? But now we don't have a node here and we don't have a node here. What do you think would be the height? If the height of the node itself is 0, what do you think would be the height of those ones which do not exist? What value should we give to them? -1, I agree with you. So -1, okay. So the height of a null node is -1, height of a leaf is 0. And we can be able to determine the other height as we go on. So that's an important thing to know. So what is the height at 15? Remember what we said? Height of a node X, the number of edges at the node, from that node to the farthest leaf on its path. So what's the height of 15? That should be 1. What's the height of 41? Height of 41? 2. Yeah, because there are 2 edges from 41 going all the way to 27. Height of 10? 3. Yeah, because there are 1, 2, 3. Height of 8? 1, and height of 3 is 0. Good work. Let's talk about balance factor. What's the balance factor at 27? Okay, 0. Okay, why is it 0? The left, well, if we go to 27, the left and the right are empty. So we say the height of empty or null node, height of empty or null node is -1. So at 27, the balance factor is -1, which is the height of the left, minus -1, which is the height of the right-hand side, and therefore this is 0. -1 minus -1 is 0. Okay, so the balance factor even here at the leaf is also 0, and the balance factor here is also 0. Why I showed you this is for you to typically understand why it is 0. It's not 0 because the height is 0. It is 0 because if we take the empty left-hand side and the empty right-hand side, and we take their heights, they are going to be 0. Remember, we're interested in the heights of the left and the right side. What about the BF here at 15? Or the BF at 15? So the BF at 15 is -1. How do we know that? Because on the left-hand side is -1 minus what's the height of the right-hand side? The height of 27. 27 is on the right-hand side. So the height of 27 is 0. So it's -1 minus 0. So the BF here is -1. What about 42? We know already 42. What about 41? What is the balance factor at 41? Balance factor at 41. That means the height at 15 minus the height at 42. The height at 15 is 1 minus the height at 42 is 0. So the answer is 1. So the balance factor at 41 is 1. You see that? It's coming up together? Awesome. What about the balance factor at, okay, so let's go to 8. So because we already saw 3. What is the balance factor at 8? The balance factor at 8 is 1. Why? The height at the height of left-hand side, which is at 3, is 0. Then 0. The height of the right-hand side is -1. So 0 minus -1 becomes positive. So the BF here is 1. What's the height at 10? Sorry, the balance factor at 10. Okay, so the height at 8 is 1 minus the height at 41, which is 2. So this will be 1 minus 2, which is -1. See that? So if we look at all these nodes here, the balance factor for them is between 0, is between -1 and 1, the balance factor for all of them. So this tree is balanced. Tree is balanced. You see how we do that? So first of all, what we did, we garnered the heights, and then we looked at the balance factors and determined that this tree is balanced. So the height at 10 is 3 because there are, how many number of edges do we have from 10 to the farthest leaf? So the farthest leaf from 10 is 27, the farthest leaf. So what are the number of edges? In fact, we can get the number of edges on the left-hand side, which is 1, 2, and then we can get the number of edges on the right-hand side, and we can get 1, 2, 3. There are 3 edges from 10 to 27, which is the farthest leaf. That's how the height of 10 becomes 3. So the height of the tree, we said before, height of the tree is the height of the root. So the root has height 3. So this tree has a height 3. Understood now? Good stuff. So that's what we do. Now, so we know that this tree is balanced. But what does self-balancing mean? What does self-balancing mean? What does self-balancing mean? What does self-balancing mean? It means maintain a balanced tree, maintain a balanced tree as you add the nodes. Maintain a balanced tree as you add the nodes. So you do not wait to create the tree. You do not wait to create the tree. You come up with an algorithm, now the AVL, or a red-black tree. You come up with an algorithm that ensures that the tree is balanced as you add the nodes. So let's see a couple of examples. Let's have some examples. Give me some values. I'm just going to write them here and then work from them. So give me some values. 8 comes in. 8 is the first one. Keep going. Give me some more. Be quick. 4. Keep going. 5. that 13, 37, 31, 7, 45, and that's 1. And I think 17, somebody else. So let's talk about those. So 8 comes in, 8 is the first one. So the root is 8. The first thing we do in a self-balanced things, we check the balance factor at 8. So we know 8 is a leaf node. So it's -1 minus -1, which is 0. So the balance factor here is 8. This tree is balanced, right? And you can all see that this tree is balanced. Then 4 comes, we stick 4 on the left-hand side of 4. And then now we check this 4. So 4 is a leaf node, so its balance factor will be 0. So because the balance factor is 0, we go to its parent and check there. So we move from the node we entered, we go to its parent, and we keep going up until we go to the root of the tree. So 4 is balanced, so we go to 8, and what's the balance factor at 8? What is the BF at 8? The BF at 8 is 1. Why? BF at 8 is, so let me write here, is 0 minus 1. So that's 1. So the tree is balanced, right? The tree is balanced because we said balance means -1, 0, or 1. So the tree is balanced here now. 5 comes in. Where should we stick 5? Where should we place 5? Right of what? Right of 4. So we place 5 here. Again, because we are maintaining self-balancing, we just check. Remember, if you did not get why we place 5 here at 4, remember we are maintaining a BST tree, a binary search tree. So when 5 arrives, 5 is smaller than 8, so we know 5 should go on the left-hand side. On the left-hand side is 4. 5 is greater than 4, so 5 should go on the right-hand side of 5. Good work. So we do the balance factor here now. What's the balance factor at 5? We know because 5 is a leaf node, the balance factor at 5 is 0 because -1 minus -1. And what is the balance factor at 4? What's the balance factor at 4? Is -1. Why? This side is -1, so the left-hand side is -1, and the height of 5 is 0. So -1 minus 0 is -1. So here, the balance factor is -1. The balance factor is -1. But what is the balance factor now at 8? What's balance factor at 8? -2, let's see. So this will be the height at 4. The height at 4 is 1 minus the height on the right-hand side, okay? So the height at 4, remember this? We said height of left minus height of right. Height of left, height at 4 is 1. So 1 minus height on the right-hand side of 8, which is -1. This is 2. So at 8, the balance factor is 2. Does everybody see how that became 2? Yeah, good. So the balance factor is 2. So is the tree balanced? No, the tree is not balanced. The tree is not balanced because there is a 2 here. Now, this number tells us that this tree is not balanced. Which side is it leaning on? Which side is the tree leaning on? Left, right? Because it's positive. Remember what we said somewhere here. If it's negative, tree is skewed on the right-hand side, and if it's positive, tree is skewed on the left-hand side. Okay. So this is, the tree is bigger on the left-hand side. So I'll write here, it's bigger on the left-hand side. So I'm going to see the problems that can arise. I'm going to say case 1. So the tree is bigger on the left-hand side. So we'll go to the left-hand side and check the left child and see what side is the left child leaning. So when you go to 4, the balance factor is -1, which means what? 4 is leaning on which side? Hello? Right. So 4 is leaning right. So we have the parent node is leaning left and the left child is leaning right. So we have left, right case. That's how we determine it. We say we have left, right case. So how would we solve that? So if you have these, solution number 1, 2 steps. Step 1. Step 1. Go to left child. Go to left child. So go to left child and rotate that child, rotate child, go to left child and rotate it left. So you go to the left child, which is this one, and rotate it left. So imagine that we are going to pull this guy this way. Okay, so what will become the parent if we did that? So, well, the root will remain the root because we have not touched it. So who goes in here? If we pull this towards the left-hand side, yeah, if we pull this towards, what is going to become the parent? So when we pull this, 5 is going to be here now, and then we have 4. Imagine like you're holding 2 things and you just, rotate them. We just rotate them. Right? So I do not suppose that the balls I had the other day. Let me look for some balls here. There's always golf balls in my house. So there's always some golf balls in my house. So imagine this was the white one now is our 4, and this one is our 5 now. Okay, this is our 4, the white one, the white ball, and the yellow ball is our 5. So when we say, so they are connected by some sort of thing, I do not see how to do that. Okay, but they are connected with something. So when we say rotate them, this will be pulling it this way. See that? So this yellow one, our 5, is becoming the parent, right? So again, this is my 4, this is my 5, and now I'm doing this. You see that? That's how I'm rotating them, like this. Good stuff. So now this becomes 5 and 4 here. And if we check the balance factor here is 0. Now the balance factor here, before we had -1, so this will be 1 because it will be 0 minus -1, and the balance factor here is 2, right? So what kind of problem that have we created? Now at 8, still we have a problem at 8, but the problem is on the left-hand side. Right here, case 2. Right here, case 2. We still have the problem. We still have a problem. The tree is still not balanced. So, but 8 has a problem on the left-hand side, and so it has left problem, and so we have to go to the left child to determine where the left child is leaning. Left child is leaning towards the left as well because its balance factor is 1. So now we have left case. That's what we have left case. And the solution to this, go to problem node, and rotate right. Go to problem node and rotate right. So what does that mean? It means go here and pull this right. If we pull right, who becomes the parent now? Who becomes the parent? 5. So 5 now is the parent. 8 becomes here, and 4 is here. Still, if you look at this tree, it's still a BST tree, right? It's still a BST tree, obeys the BST property. But now if you are to do the balance factor here at 4 is 0. BF here is 0. BF here is 0. And BF here is what? Is 0 minus 0 is also 0. The tree is balanced. So far, so good. Anyone with a question? Let's go on. So now, so 13 then comes. 13 will stick it here. I want to transfer this tree to the other side. Sorry about this because there's no space there and I don't want to delete these things. So we have 5 now. We have 4. We have 8. And 37 comes. That 7 goes in here. Again, we can check the balance factor. Balance factor at here is 0. Balance factor at here is what? It's minus 1, minus 0. So this minus 1. And at 5, the balance factor is 0, minus 1, which is minus 1. The tree is still balanced. 31 comes, so that 1 should go here. That's correct, yes. So we use the height to determine the balance factor, and then we use the balance factor number to determine which way it needs to rotate to maintain balance. That is correct. That is very, very correct. So we go to 31. The balance factor at that 1 now, so remember, it's self-balancing. So we have to keep balancing. Every time we add a node or we remove something, we have to keep checking that. So we go to 31. We check the balance factor is 0. The balance factor at 37, the balance factor at 37 is 0 minus 1, so it's 1. The balance factor at 8 now, so we're updating them. The balance factor at that 1 now is minus 1, so it's minus 1, minus 1, so this is minus 2. Okay, so we have problem here. Okay, because here is minus 2. So we determine what problem it is. It's minus 2, meaning that the tree is heavier on the right-hand side. So I'll say here case 3. Looks like it's going to be a case 3. So at 8, we have a minus 2. So it means the tree, the problem is on the right-hand side. So it has right problem. And then therefore we go to the right-hand child, that is 7. We look at the balance factor is 1, meaning that at 37, the tree is heavier on the left-hand side. So we have right, left case. Oh, by the way, I should have written here, I said step 1. Step 2 really is this now. Go to problem node, go to initial problem node. That's step 2. Basically, after you have left right case and you rotate left child towards the left, then you get left case, and then you just rotate to the right. So for right left case now, which is what we have up here, then we need to come up with some solutions for it. Okay, so what do we do? Because of right left case, again we have 2 steps here. Step 1, go to left child, and rotate right. That's step 1. Step 2, just similar to this other one. Step 2, go to initial problem node. and rotate left. Okay, see, let's see that in operation. So we go up here. So the first thing, step, go to left child and rotate right. So we go to the left, right child. We had right. So this has a right problem. So we go to right child. I don't know why we wrote down. Yeah, because the right problem. So right, left case. So we go to right. Did we have that? So this is right. So we go to the right child. The right child is here. So right, and then this one has left. Okay, so we go to the right child. And once we go to the right child, we rotate that child right. Similar to here, we went to the left child and rotated that child left. That's the same thing. So we go to the right child, which is 37. And now we rotate this 37 towards the right-hand side. So think about it being like this. Okay, so this is that 7. The white ball now is that 7. And when we say rotate that towards the right-hand side, which is my side, which this side now, so we are like this side now. So I'm doing this way, right? I'm pulling this that way, that way. So 31, this one becomes the parent. So now, if you think about it, I'm putting this down. So my tree now will look like this: 5, 4, 8, that 31, and then that is 7. See that? 8, that's 1, and that is 7, because I pulled this way. Now, if you look at this now, if you check the balance factor here, this will be 0. The balance factor now here will be what? Will be -1. And the balance factor here will be what? Still -2. Correct? And now, if you look at that case, what kind of case is it? Going with what I was writing before. What kind of this case is this? This is a problem node. We go to the problem node. To determine cases, normally you just go to the problem node. The problem node says left. Sorry about that. The problem node is negative, so this means right. So we go to the right child. The right child, the balance factor is -1, so also means right. So this is right case. Now we have right case. To solve this problem, go to problem node. And rotate left, which is basically our step 2 here. It's our step 2. Go to problem node and rotate left. So the problem node is 8. We rotate 8 left-hand side. So let's see how it works. So now here we'll have 5 still here. We'll have 4. And now when we pull 8 down, that 1 will be the parent. And then here we'll have 8. And here we'll have 37. Yes, always the most negative or the most positive. You remember here, it was the most positive. Here, I think it was 2. So when we had, when it's left-right case or left-left case, the problem node is the one most positive. If we have a right-left case or right-right case, the problem node is the one which is most negative. Make sense? So for example, here it's -2. And the other one was left case 2. So if you look at this tree now, the tree is balanced again. Is it making sense now? So these are the main, or these are the only cases or problem cases that you have. These are the problem cases that you have. There are 4 of them. Case 1, left, right case. If you encounter these, you go to the left child and rotate the child left. So left. Where did we get that problem? So we have left and then right. So we went to the left child and rotated right. So we have left right case, we have left left case, we have right left case, and right right case. So the idea with these cases, case 1 and case 3 here, is basically we want to correct the problem. So if it was a right left case, we want to make it right right case, so that then we can just go to the problem node and rotate left. If it's a left right case, we want to go to the left child, make the problem a left left case, and then rotate the problem node towards the right to solve the problem. So far so good. Now let's make another thing now, just to show a couple of things. So we had 7 coming through. So let me write this down. We have 5 here. I think we have that. We have. Let me put that problem. We have 5. We have 4. So we have 5. We have 4. We have 31. We got 8, and we got 37. Then 7 comes and goes up here. Okay, we check the balance factor. At 7 is 0. Balance factor at 8 is what? Is 0 minus 1, so it's 1. Balance factor at 31 is 1 minus 0, so that's 1, right? Balance factor at 5 is 0 minus 2, which is minus 2. Right? So at 5, we have a minus 2 problem. Remember, we're only going on one side. Where we add the node, we just go trace our path back to the root, and then we determine that. So it's minus 2. So we come up here and say, oh, what problem is this one? At 5, let's determine what the problem it is. We have a negative side, so it means this is a right problem, right hand side. So we go to the right child, we find the balance factor is 1, which means at that 1, we have more nodes on the left hand side. So this is actually a right left case. So you see, once we determine that, we know what to do. Right left case means go to the right child and rotate right. So we go to the right child, which is that 1, and rotate these children right. So this will become, we rotate it right. So we'll have 5, we'll have 4 here, we have 8 now with 7, and then we have 31 and 37. And now if you look at these, now these are right case. We go to 5 and rotate 5 towards the left hand side. Now, this is a step I want you to check. So normally, if you rotate left, the left children of the right child will become children of the node that's being rotated. So this is an important thing here. When you are rotating this child, rotating left means children of right child, children of right child, children of maybe not children, means left hand side children of right child becomes children of parent node. I know that's a mouthful. So rotating left means left hand side children of right child becomes children of parents. What does that mean? At 8, the children on the left hand side should become the children of this parent node here. So that means if we rotate this towards this side, this then becomes 5. Sorry, 5 gets rotated. 8 becomes a parent. 5 becomes a parent. And then we have 5. The left children of 8, 7 becomes child of this node. And here we have 4. And now here we have 31. And we have 37. So again, if you look at the tree, it's a BST tree. At 8, all the nodes on the left-hand side are smaller than 8. And on the right, all the children are greater than 8. So that's how you see that coming through. Are there questions for me? Similarly, if we had the same kind of problem, the same kind of problem, we would also correct those problems the same way, right? If we had the same kind of problem that required that, on the other side, for example, rotating right, if we are rotating something right and we had some children on the left child. So this is what it means here. If we are rotating right means right children or right child of the, so rotating right means right children of the left child becomes children or left children becomes left children of parent node. Actually, this is an important thing. Write them down somewhere. These are important. So rotating right would mean right children of the left child becomes left children of the parent node. So, okay, so I'm going to stop there with these actually. So we have learned today how to do the balancing and we have learned the case for those 4 cases as performed with the AVL trees. So I'm going to stop there with this. Let me stop this share for now. If you go to Blackboard and you go to the link where that material is, you will find an animation. In that animation will contain the AVL tree. I can play it for you for a few minutes. Let me see whether I can open it up. So 1 minute is coming up. PowerPoint sometimes takes a bit of time, so maybe I should play with something else. So if you go to Blackboard, you'll find something like this. I'm not particularly certain that we can have the animation come again. Okay. So you're going to find an animation like this when you go to Blackboard, and that animation is going to show you when items get added, where the problem comes in, and how you do the rotation to resolve the problems. Okay, so you're going to see that when you go to Blackboard. I do not have the time right now to go through it. So if you revisit the material from today's class, and you revisit the notes on Blackboard, then all that material should be able to help you to do the quizzes, and not just the quizzes, but also to learn how these things are done. I will have the PDF for this class posted onto Blackboard, so you'll be able to play around with it. If there are not any questions, the class will end there.